Start recording. Okay, so let's start our next talk. So let me introduce Yipeng Wang from Columbia University, who will tell us about the filling problems with scalar curvature constraints. So Yipeng, you can start whenever you're ready.
Yeah, thank you for this kind invitation to this workshop. Um, so I guess Sven was just talking about something kind of related to what I'm gonna say, but I still want to just give some like different perspectives. Like it's like a different problem, but there are some similarities which you can see later. The how to So I want the goal mainly I want to talk about is about scalar curvature on a manifold with boundary. So as you may know that on closed manifolds, there's usually some kinds of there are all kinds of obstructions of metric with positive scalar curvature. Like for example, the torus cannot admit a metric with positive scalar curvature. But on manifold with boundary, in general, you don't have such kind of obstruction. So it's a very early result by Gromov on which states that on basically saying that for any compact manifold with boundary, you can always find a metric with positive scalar curvature. Even you can make it to have positive sectional curvature. So the proof is based on H principle. So this is it's kind of different than a general case of manifold that's closed. And moreover, not only you can state such a result about just Riemannian metric on manifold with boundary, you can also say something about an induced metric on the boundary. So it's due to Wang and Wei. In 2020, they proved that so you have a compact manifold M with boundary, and then you fix any Riemannian metric on a boundary sigma, then this metric can always be extended to a Riemannian metric inside, and that emits positive scalar curvature. So not only you can just construct any metric inside, but you can also impose its boundary conditions. So basically, this is saying that just to impose the boundary metric would not give you any obstructions of positive scalar curvature metric inside. Okay, so what I would like to address today is just to study any obstructions to these kind of fill-ins. So namely, you have a manifold and you have a filling manifold, which the boundary is given by the manifold you are starting with. And you want to look at fill-ins with scalar curvature bounded from below. Are there any obstructions to that? So this is the sort of the main character I would like to discuss today. So these type of questions regarding fill-ins are kind of sort of goes back to some very early works, and that sort of have a very general setup. The general idea is very broad is to kind of investigate the relationship between the intrinsic curvature and the extrinsic curvature. So you have a manifold with boundary, and then you have then you study the intrinsic curvature, to defined by this curvature tensor on M, and then you want to study the relationship between its extrinsic curvature on the boundary, which is defined by the second fundamental form. So it's roughly like a second derivative of your metric inside and the normal derivative on the boundary. You should expect there are some relationship between these kind of things. So this is a very general this is a very general scheme. Okay. And then so Gromov in 1996 imposed this following process, which he called the filling problem, and then he also stated in a kind of vague setup. It's not extremely precise, but let me try my best to explain it. So you started with a closed manifold, a closed Riemannian manifold, and then you fix a symmetric two tensor K, and then you look for every possible Riemannian manifold one dimension higher, such that the boundary is given by this closed manifold you're starting with, and you prescribe the second fundamental form K. So you have so essentially you are fixing the boundary data, and then you look for every possible this fillings. And then so among all these kinds of fill-ins, you try to maximize the curvature of M. So what does curvature mean? It could simply means anything you want. You can study sectional curvature, Ricci curvature, scalar curvature, whatever you want. And in this context, if it like whenever it makes sense. So whatever curvature constraint you want to specify, then you try to maximize this curvature constraint, and among every possible fill-ins that sort of satisfies this condition that I was just talking about. And then this will define sort of like an invariant associated to this triple of data. So you have a closed manifold with a metric and a symmetric two tensor that serve as the second fundamental form of the boundary. Okay, so this is the fill-in problem. And again, this is stated in like a very, very general context. So it's very reasonable to expect like in general you wouldn't get anything. But let me just focus on a case on scalar curvature for the moment. So for the context of scalar curvature, so let us instead consider the following. So let us fix which this terminology I will explain a little bit later, which is I call it Bartnik data, which is a triple of data of a closed Riemannian manifold with a given function on this manifold, which I denoted by H. So the idea is that will serve as the mean curvature of a fill-in of Riemannian manifold. So you look for every possible Riemannian manifold M and G that fills your boundary sigma, and with this mean curvature H. Okay, and then you try to maximize the scalar curvature among every possible fill-in. So you want to look for the infimum of the scalar curvature. So, and then you try to maximize these this quantity. So you look for, so given a fill-in, you try to see what's the lower bound of the scalar curvature, and then you try to see how far you can sort of push this lower bound above, and that defines this invariant kappa. So this kappa is an invariant associated to sigma, gamma, and H. And then you want to see what's like the relationship between kappa and this triplet of data. So under this context, so Gromov imposes the following conjecture. This is a very very, very general conjecture, which is what I'm going to talk about mainly today, which says that if you have a fill-in of Riemannian manifold with boundary with scalar curvature bounded below by some constant kappa, then what you should expect is that the integral of the mean curvature is always bounded by some constant. So this constant on the right-hand side depends on the boundary sigma, gamma, and kappa, but it does not depend on the metric G. So this is saying that this integral of the mean curvature of this fill-in would not depend on the specific metric you're looking at, but just its scalar curvature lower bound. So this is yeah, if you think about this, this will sort of tell you like give you like an obstruction of a fill-in of this given scalar curvature bounded from below. Okay, so this is a very general conjecture. And then what I will try to talk about today, I'm gonna impose this this little extra condition, namely the mean curvature is positive. So I will explain later why we need this extra piece of information. And then so we'll consider mainly the case where kappa is negative because if I mean if this conjecture is true for some negative kappa, then it's also true for kappa 0 or some positive constant. But you just need to understand what exactly the constant is, and then you can always sort of rescale in kappa so that it's equal to minus n times n minus 1. Okay. So before I sort of move on to the to study some specific cases for this conjecture, let me try to take a small digression to some alternative aspect of this problem, which this is sort of from the perspective of relativity. So I'll just give a very general introduction. So we know that so in relativity, this the scalar curvature in relativity can be sort of interpreted as a notion of the local mass density. And this famous positive mass theorem just saying that if you have an isolated gravitational system, if the local mass density is non-negative, then the total mass should also be non-negative. It's very intuitively makes sense. And then if I translate it into a mathematical statements, this isolated gravitational system are sometimes are modeled by asymptotically flat manifolds. So in particular, it's a complete Riemannian manifold with sort of the integral of the scalar curvature is bounded, and then outside a compact set, you can sort of model it on the exterior of a ball in the Euclidean space, and then you have a given asymptotic expansion of your metric. So the first order term is the Euclidean metric, so it's asymptotically the Euclidean metric and with some lower order term. And then under this context, this mass quantity can be just defined by this flux integral. So you look for since we're asymptotically flat, as you go to infinity, you can look at these coordinate spheres and then you evaluated these flux integral. And then this will sort of defines your quantity that's actually independent of the coordinate that you're actually choosing. So it only depends on this metric G, this asymptotically flat metric. Okay, so then the positive math theorem is just simply if I translate it into this mathematical statement, it's just saying that if you have an asymptotically flat manifold with non-negative scalar curvature, so if G has non-negative scalar curvature, then this quantity M is actually non-negative. And then you have equality if and only if your manifold is actually isometric to the Euclidean space. Okay, so why do I want to talk about this? So this okay, so this definition I'm stating right here in the physics literature defines the mass of this asymptotically flat manifold. So the idea is that you're sort of going far away from infinity to see this entire the system that you are looking at, and at that point you can try to evaluate the mass. But then in the also in the physics literature, you not only just want to evaluate a mass just for the entire system, you also want to understand on, let's say, if I have a bottle of something, what's the mass of this thing, right? So that's the notion of a quasi-local mass. So let me explain it a little bit. So the purpose of defining such quantity is just to evaluate the idea of how much mass is contained in the given region. So the idea, okay, so now I will come back to this terminology. So it's originally due to Bartonek to explain how to do such evaluation, where he suggested a potential way just to defining such quantity, which kind of makes sense in in the physics literature as well. So what you do is you started with a closed you start with a Spartanic data. Recall that that's just a closed Riemannian manifold with a given smooth function on it, and you look for which I call admissible extensions. So what I mean by this admissible extension is that you look for an asymptotically flat manifold whose boundary sort of is identified with this thing sigma. And then this asymptotically flat manifold has non-negative scalar curvature. And then when you sort of adding this asymptotically flat manifold from the outside, you want this mean curvature to be bounded from above by this function eta that you are given here. And then you want to add this this slightly extra condition, just a little more a small technical condition, which just preventing you have a black hole region inside. So saying that the sigma is not enclosed by any outermost minimal surface. So what you want to do is, okay, you started with the Spartanic data. You looked for every possible admissible extensions, namely all these things satisfying this these four properties here. Then you try to define the quasi-local mass of this region, just defining as the infimum of the ADM mass over all these admissible extensions. Right, so you consider every possible extensions, evaluate the mass at infinity, and then take the infimum of that. Okay, so the one of the key advantage of doing that is that because by the positive mass theorem, these possible extensions will have non-negative mass, and therefore when you take the when you try to take the infimum, these quantity associated to sigma, it also has non-negative mass. So this is one of the crucial property that you want to have for these type of quasi-local massing. You want it to be something that's non-negative. Okay, and finally, I should also mention that so this is just one approach to this problem. I mean, it's there are a lot of works regarding this quasi-local mass problem in general relativity, and there are also different formulations proposed by different mathematicians and physicists, including Sir Roger Penrose, Stephen Hawking, Brown and York, and also Gersh. So we'll also talk about the alternative formulation, D2 Brown and York later, and then you will see that there are some, in some sense, different definitions will also be equivalent under some situations. Okay, so now I'm gonna explain a little bit how these two things, these Phelan problems and these quasi-local mass things are related together. So before I doing that, so when I try to explain these extensions, well, one question you may wonder is that does such extension even does it have to exist? And in general, this is actually a very hard question to study if you don't impose anything else. So the work by Shi and Tem showed that if your boundary data can be isometrically embedded into Rn as a strictly convex hypersurface, then you can always find this extensions. And for any this function eta that's positive. And then under this situations, so namely when you are looking at your boundary data to be a strictly convex hypersurface in a Euclidean space, there's another notion of a quasi-local mass defined by Brown and York. So what they did is they just associated your triplet to be this quantity, namely given by the integral of your boundary of H0 minus eta, where H0 is the mean curvature with respect to the Euclidean metric. You can always have it because you are assuming that your boundaries can be embedded into Euclidean space. Then so the work of Shi and Tem also showed that if the region you are enclosing by the sigma has non-negative scalar curvature, then the Brown-York mass is actually non-negative. So let me state it, the result in this form. So you started with a strictly convex smooth domain in Rn, and then you consider an arbitrary Riemannian metric G. So G is not necessarily the Euclidean metric, but it satisfies the property that it has non-negative scalar curvature inside, and then the mean curvature with respect to G at the boundary is positive, and then you want the restriction of your metric on the boundary agrees with the Euclidean metric. So you don't, G is not necessarily the Euclidean metric, but you only impose that the boundary metric agree with the Euclidean one. Then under such conditions, you can evaluate this quantity, which is just the difference of the mean curvature, and then you integrate it on the boundary. And this difference always have a sign. So this is how they so this will imply that this Brown-New York mass is non-negative. And then moreover, they also showed that if you're in a Euclidean, if you're in an equality case, if and only if you are actually in the, if you're actually in the case where G is a flat metric. Okay, so let me describe a little bit about the idea of the proof, because as we'll see later, the general this sort of general machinery works for like a lot of different contexts. So let me just use one page to explain how the proof goes. So so what they start to do is they consider so-called a quasi-spherical metric, G tilde, that's defined outside omega. So recall that omega can be sort of embedded into the Euclidean space, and then outside omega, you try to construct a metric that outside that sort of glues to your original metric G. And this terminology, quasi-spherical metric, I'm probably gonna explain it a little bit later, but it's just a metric that satisfies certain conditions. Okay. So you wanted to agree with the metric G on the boundary, and then you want the mean curvature of these two metric at the boundary of omega would match. So therefore, you can sort of glue this metric inside omega. I mean, from the outside region of omega. And then so by this quasi-spherical metric, you want this metric G. Well, it will satisfy the property that this G tilde will be asymptotically flat, and it's actually scalar flat. So the scalar curvature of G tilde is 0, and then and the metric you have is an asymptotically flat metric. And moreover, Xi and Tam consider this following quantity. So they cook up a quantity that is monotone decreasing, such that if you evaluate it as 0, it's given by this this quantity you want to control, namely the difference of the mean curvature integrated over the boundary. And then as this R go to infinity, this quantity will converge to the ADM mass of this G tilde. So this of this metric that you are like putting right here. And then this quantity is monotone decreasing. So in particular, you know that this quantity evaluated as 0 will be bounded from below by its value at infinity, which is given by the ADM mass. But then by the positive mass theorem, the ADM mass is non-negative. So therefore, this proves this this estimate of and the non-negativity of the Brown-New York mass. Okay, so so now let me get back to the actual fill-in problem that I started to talking about. So how is this this problem related to the fill-in problem? So if you think about it, the thing I just mentioned in the previous page, this result by Xi and Tam, actually tells you that this Gromov's fill-in conjecture is true when the case you are looking at non-negative scalar curvature. And under the specific case where your boundary bounds a convex region in the Euclidean space. Because and also in this case, well, your boundary is diffeomorphic to the sphere because you are understand it as a strictly convex domain in Euclidean space. And then what you bound, the region you bound is given by a ball. Okay, so this general aspects tells you that if you can prove the positive math theorem with some kinds of data at infinity, then it's possible to use this idea of Shi and Tam to prove this filling conjecture. So under this spirit, in 2021 by Liu, Shi, and Zhu, they showed that you can also prove the filling conjecture if your boundary is not necessarily diffeomorphic to a sphere, but you can also allow it to be diffeomorphic to Sn-1 cross S1 or Sn-1 cross the two-dimensional torus. So you can allow to have an extra torus factor up to 2 dimensions. Okay, so the way to do it, it's very similar, which just relies on the positive math theorem, but not on asymptotically flat manifold, but asymptotically locally flat manifold. So the infinity sort of looks like these two things, so a sphere cross a torus. Okay, so this is the case for asymptotically flat things. Namely, it will give you the filling conjecture when you look for non-negative scalar curvature fill-in. So the conclusion is that the integral of the mean curvature will always be bounded by the integral of the mean curvature if you just fill in by the Euclidean data. So that gives you the upper bound. And then for this thing I want to talk about, if kappa is negative, so what you can expect is that it will sort of relate it to the asymptotically hyperbolic positive math theorem. So you want to look for scalar curvature filling ends with negative scalar curvature. Then you try to then what you should expect is to see positive math theorem, but on asymptotically hyperbolic manifold. Okay, so let me just give a little bit of the background of asymptotically hyperbolic manifolds and its positive math theorem. I mean, it's quite similar, but there are some technical issues to make it more involved. So what you started with, you consider the conformally compact hyperbolic space. That's our model metric. Then I say a Riemannian manifold is asymptotically hyperbolic if you have the following kinds of asymptotic expansion at infinity. So notice that in this coordinate system, the infinity corresponds to as this parameter as going to 0. So G is that at the asymptotically hyperbolic if you have such kinds of expansion where the first term is just a hyperbolic metric and the next term is given by this given power and then defined by some symmetric two tensor defining on the sphere. So which is the conformal this is the conformally compact boundary at infinity. And then the positive math theorem in this case is that if you have scalar curvature at least minus n times n minus 1, then the mass, well, in this context, is not negative. So what is the mass defined? So you just take the next term, which is this two tensor Q of your asymptotic expansion. Well, Q, well, in general, it's not necessarily a multiples of the identity. So you're gonna evaluate its trace and then you try to integrate it on the conformal infinity. And this sort of defines the mass quantity. I mean, if you look at there are several different definitions of the mass, and then you can try to see that this is actually very similar to the one that I was explaining a little bit earlier on the asymptotically flat case. You also try to integrate some quantity going out to infinity. Okay, so that's a hyperbolic positive math theorem. And there are some earlier works due to Yipeng Wang, Kircher, Herzlich. I'm not stating all of the works, but just some of the important progress on this, and then also Anderson, Tsai, and Galloway, and also Kircher and Delay. Okay, so knowing this the positive math theorem on asymptotically hyperbolic manifold, so using the same machinery, you can also obtain this filling conjecture under the context with negative scalar curvature. So what you can do is that you can consider the case you're filling in a sphere with a ball, and it's due to Shi, Wang, and Wei. So they actually proved the following two results. So the first result, it's saying that, okay, so the general statement for this result is that the filling conjecture is true under the context of if you are filling in a sphere by a ball and with scalar curvature at least minus n times n minus 1. And moreover, if you are trying to fill in where your boundary data is actually just given by the round metric of the sphere, then you can compute the sharp constant of this filling. So this is the first theorem I'm stating here. So it says that if you're also impose your boundary data to be exactly to be the round metric, then the integral of the mean curvature will bounded by this explicit constant. It just depends on the dimension. And then in general, if your boundary data is just some arbitrary metric on a sphere, then you can also show that for any fill-in with scalar curvature at least minus n times n minus 1, there is always you can always bound the integral of the mean curvature by some constant. Just depends on the boundary metric, but not the but not the metric G inside. Okay. So now I would like to talk about the main result. I would just try to explain. It's still on this asymptotically hyperbolic context, but then instead of looking at the sphere, we look at a different model, which is a torus. So that's sort of like the next simpler case that you can try to think about. So we consider the fill-in of sigma, which is given by S1 cross Tn minus 2. So it's a torus, and which I sort of distinguish out the first S1 factor, so that I'm filling in by a disk cross a torus. So M is B2 cross Tn minus 2. And I'm looking at the dimension where it's from 3 to 7, because as I'll explain later, it's sort of involving the regularity issues of minimal surfaces. And then let me define this quantity. So if I give you a metric this gamma on the boundary, let me define the sigma to be the systole of this corresponding distinguished S1 factor of gamma. Whilst the systole is just like the length of the shortest curve that sort of spans this S1 factor in sigma. And then let me assume that inside M, the scalar curvature is at least minus n times n minus 1, and in the boundary is mean convex, so H is positive. Then we have a very similar result than this previous Shi-Wang Wei result that I was explaining, namely the fill-in conjecture is true in this context. Namely, you can bound the integral of H of the boundary just by the boundary data gamma. And moreover, if you have a flat metric on the boundary, so if you have so suppose that gamma is some flat metric on the boundary torus, then you can actually compute the sharp constant. So namely, the integral of H minus n minus 1 is bounded by this constant. Just depends on the boundary data. So in particular, you can just state it explicitly involving the volume of the boundary and the systole quantity I was explaining. Okay, and then so as you might expect, to prove such a result, you will need some kinds of positive math theorem, as I was trying to explain this philosophy slightly earlier. But now we're looking at the context of asymptotically locally hyperbolic manifold. So what you can do is that you can start with the model metric, which is this hyperbolic metric on essentially this cost metric on B2 cross Tn minus 2. So you fix some flat metric on the boundary, and then you consider this hyperbolic cost metric. then let's say a Riemannian manifold is asymptotically locally hyperbolic if well, you can also impose this condition, so you can the first order of the expansion is just this hyperbolic metric, and the next order expansion just giving you this quantity defining by some symmetric 2 tensor on the boundary, and then with this given power. And then you can define mass of this quantity, this asymptotically locally hyperbolic manifold in a very similar way. Recall that in the previous case, I was explaining this definition by Yipeng Wang. In the asymptotically hyperbolic case, you just integrate this the trace of the next order expansion of your Riemannian metric, and you integrate it at the conformal infinity. So now we're doing exactly the same thing right here. So that's the mass defined in under this context. So the main difference is that unlike the hyperbolic case, so this mass could actually be negative. So this is quite striking. So it's so you can actually construct like a very explicit metric G that satisfies this condition, and then you can evaluate the mass explicitly such that this quantity is negative. So let me explain. Maybe I'm not gonna I will try to maybe skip a little bit on this slide. So so the construction of this counterexample to the positive mass theorem under this context is due to Horowitz and Myers in early 90s maybe. So what they do is they consider that this doubly work product metric. So let me not go into the detail. Then they use a change of variable so that they can write it in under this context where it is asymptotically locally hyperbolic according to my previous definition. Then well, that the metric they define was sort of defining in the outside region, and they showed that if you normalize the systole of your boundary torus, then you can if you do that in the right way, then you can extend it to a smooth metric on R2 cross Tn minus 2. That's asymptotically locally hyperbolic and with constant scalar curvature minus n times n minus 1. And then they can compute this expansion at infinity explicitly, and that defines this 2 tensor Q defining on the boundary. And then you can explicitly evaluate that the trace of Q will be something negative, and it will be something depending on this the systole quantity sigma here. So in particular, this says that this mass could in general be negative, but there's this great result last year due to Brendle and Hung. Well, they showed that so the mass, although it could be negative, but this metric construct by Horowitz and Myers is actually the one among every asymptotically locally hyperbolic manifold that has the lowest mass. So in particular, every asymptotically locally hyperbolic manifold, its mass has to be at least the mass of the corresponding this Horowitz-Myers metric. And they proved this result for in dimension 3 and 7, and they also proved this the corresponding rigidity very recently. Okay, so this is saying that the mass could be negative, but you still have this sharp lower bound on the mass that just depending on the boundary. Okay, so so a few more words about how they proved this conjecture. So this positive mass theorem, what they did, they prove it using the following systolic inequality. So what they do is that if you have they show that if you're on a manifold given by a disk cross a torus with scalar curvature at least n minus n times n minus 1, then you can show that the infimum of the boundary of the mean curvature minus n minus 1 is always bounded by the systolic quantity. So that's that is sort of like this crucial geometric quantity that gives the positive mass theorem. And then the proof of this, it's very similar to this Shen-Yao's technique on this minimal surface slicing, but this one relies on like a free boundary minimal surface. So in particular, it also has this regularity issue. So it's only so far it only holds in this given dimensions here. Okay. So now I would like to describe how to use these results to prove our main to prove our main theorem regarding this integral mean curvature estimates. So the key strategy follows follows similarly to Shitam. So what do? So let me consider the case to how to compute this sharp result first, and then I will explain how to deduce the general case. So you started with fixing a flat metric on the boundary torus, and then you consider a metric of the following form. So which is given by this War product with an undetermined function u, that's not yet determined, on these outside regions, so sigma times 1 to infinity. So in particular, if u is exactly 1, then you are just giving back to the that is exactly just the model metric. So what I want to do is to solve the following equation. So I was explaining this terminology called the quasi-spherical equation. So it just says that I want to prescribe the scalar curvature of this ansatz G to be minus n times n minus 1. I mean, everything is quite explicit here besides this function u I haven't determined it yet. So what I want is that I just want to solve the equation such that the scalar curvature is minus n times n minus 1. And then I want the initial data sort of to be something that matches my mean curvature of the filling in that I'm trying to have. So that will give us like the following nonlinear parabolic equation in this form. So I mean it's not an easy equation, but you can still manage to solve it. So what you can show is that if you started with any positive initial data, the solution will exist for all time. So if you look back, our initial data is exactly given by n minus 1 over the mean curvature of a given filling in that we are trying to have. So in particular, this is the reason that why we need this extra condition of the mean curvature to be positive. This is also coming up in the original work of Shi and Tam. So just on the slightly technical issues here. So you can show that the solution exists for all time, and then you can show under some parabolic estimates, you can show that as r going to infinity, this u actually goes to 1. So recall that if u is exactly just 1, then you will just going back to the exactly the hyperbolic cos metric. So if u converges to 1, then this roughly means that as r goes to infinity, your metric looks closer and closer to a hyperbolic metric. So this roughly tells you that G is asymptotically locally hyperbolic. But so far, I'm not. I mean, I think it should be true, but it's not exactly true that you can show that it's actually asymptotically locally hyperbolic under the definition that I was explaining. So that's a slightly different caveat here, that you cannot directly apply the positive mass theorem by Brendle-Hung. But instead, what you're going to do is to apply this systolic inequality. So let me explain how to do that. So what you do is that you can instead derive an asymptotic expansion of u. So as I just said, u will converges to 1 as r going to infinity, and then you will have a next the next order term is given by some smooth function defining on the boundary. And this asymptotic expansion, if you write it out using this ansatz metric, this tells you that if you look at this each r slices of sigma with respect to G, then this tells you that the mean curvature of each slice has this asymptotic expansion. So the first order is given by n minus 1, and the next order is something that depends on this function mu that you're looking at. Okay, so now the idea is that I would like to apply the systolic inequality to the slices, but a small issue is that this function mu of x, recall that this is something just defining on this torus. This is not a constant function. So what you do is that you can use some machinery to sort of to find a nearby surface such that the mean curvature, well, it even in the next order, it will be like a constant mean curvature surface, and then it will have some very small order error term. And this mu zero is just the average of mu over sigma. So in particular, mu zero is some constant that depends on that does not depending on R, but just defining on the boundary. And then the idea is that if you try to apply the systolic inequality to this perturbed surfaces R going to infinity, it will tell you that this minus and minus one mu zero is bounded by this given constant depending on the systole. So recall that the systolic inequality says that the infimum of mean curvature minus and minus one is bounded by such a constant. And in our case, the infimum of mean curvature, since our surface is almost like a constant mean curvature surface. So this this mean curvature, no matter if you pick at any points, they will always be very close to sort of to each other. And therefore, you can when you try to evaluate the mean curvature, this excess of mean curvature by n minus one, what you will see is just this constant mu zero, and that gives you this estimates on mu zero. And then you cook up this quantity m of R, which also appears in my earlier slides in a work of Shi and Tam. So you define it to be the integral of each slice of h minus n minus one, and then you normalize it by multiplying R and dividing by the volume of the boundary. So as you see, this is exactly the quantity you try to evaluate, and then the PDE that you satisfy would then imply that this quantity m is monotone increasing. So you also have like a monotonicity in this case. Okay, then what you can do is you just evaluate the quantity m of one, which is given by this quantity h minus n minus one, integral of h minus n minus one. This is something you want to control, and then you evaluate the quantity at infinity, which, if you recall, what's the expansion of the mean curvature at infinity, it will actually converges to this constant mu zero. And then therefore, by combining with this monotonicity, that tells you that you have this integral mean curvature estimate. Okay, so maybe in the last 2 minutes, so this is how you do the case where the boundary is a flat metric. So this gives you a sharp constant of this integral of h minus n minus one, depending on this the boundary system. So the general case, the general case sort of can be reduced to the case of a flat metric. So what you do is that if you have an arbitrary Riemannian metric on sigma, then you can choose another flat metric such that it's sort of larger than my original metric. And then what you do is you also consider something that interpolates between the two metrics. So you also have this sort of Kolar region that's defined on the sigma cross an interval, and of this form. So this gamma t is just linear interpolation between gamma and gamma hat, and then I have some function v here to be determined later, which I would determine v exactly as I did before by solving this quasi-spherical equation. But this is a slightly more involved case, which because this gamma t it's something that's pretty abstract, that just depending on these two metrics here. So you can still try to solve for V by imposing the scalar curvature. And what you can show is that under this color region, you don't that this integral of mean curvature does not lose too much. So the integral of mean curvature with respect to G will be bounded by some constant multiplied by this integral of mean curvature of G tilde. Namely, that's the thing that you are trying to gluing in this color region. And with this constant that just depends on the metric gamma and gamma hat, but nothing else. Then if you try to choose your initial data appropriately, then you can try to glue in this color region to your original manifold. So originally, I just have a solid torus with a boundary metric I don't know, and then I glue in this color region. So that will also give me a solid torus, but then it's integral of the mean curvature of the bound. But then the boundary data is now a flat metric, which is given by this gamma hat. And then after gluing in this process, this integral of mean curvature will only sort of increases not too much by some constant that just depends on your metric and the metric that you are also this flat metric that you are gluing in. And then you can and such a gluing machinery, there are a lot of ways you can do it, either by Brendel, Marcus Navis, and also Beer and Henke has some words to do that. And by doing that, that will reduce us to the case that I was just talking about slightly earlier, when your boundary is a flat metric, and then you can just apply the result there, and that shows that the integral of the mean curvature is always bounded by this constant. Okay, so yeah, I think I'll probably just stop here. I'm sorry, I think I might have a little bit over time, but yeah.
All right, thanks for the interesting talk. Any questions from the audience?
So in your proof, you obtain a function mu x, and you have changed it to a constant mu 0. And why is it necessary to do so?
Let's see. Wait. So can you say that again?
Yeah, so you obtain a function mu x, and you say it's not generally a constant. You have to make it to a constant mu 0, and why have you to conduct this step?
I see. So yeah, that's a good question. So the idea is the following. So I would like to okay, so I want to apply this systolic inequality. So what does the systolic inequality say? It says that if you have a solid torus with scalar curvature at least minus n times n minus 1, then you can bound the infimum of the mean curvature of the boundary. So
yes.
So if you think about that, that gives you that tells you can always bound the infimum. But what I want to do is I want to bound the integral of the mean curvature. So how to interpolate between from the infimum of the mean curvature to the integral of the mean curvature. So you can do that if your mean curvature is almost a constant. So everywhere that that means your mean curvature is almost like is very close to this infimum, which is the thing that you can control.
Oh, okay, thank you. And I'm also interested in what does here the perturbation sigma hat r exactly mean?
So what you can so what you can do is that you have, so for each r you have a sigma r.
Yes.
Then what you do is you can just try to so what you do is you can just look for maybe like a normal graph over sigma r.
Okay.
that defines the
So-
surface, and then you
so
choose the
this-
graph. Yes.
Mhm. So you just construct a new surface in the same ambient manifold.
Yeah, exactly, yes.
Okay, thank you very much.
Exactly, yes.
Okay, any other questions? All right, if not, let's thank the speaker again. All right, great. We just have one more to go. Yeah, stop recording.